Alright, so let's talk about trigonometry for a bit. There's basically two ways to do it, I would say. The one is just with real trigonometric functions, so I'll start with that. So you can derive one or both of these using the law of cosines in the right picture. If you want me to show you how to do that, just ask me sometime. Glad to show you. Cosine theta plus cosine theta sine beta. This is the adding angles formula for sine. Now, if you differentiate this, right, with respect to theta, fixing beta as a constant, what happens? Well, you get cosine theta plus beta equals cosine theta, cosine beta, derivatives cosines minus sine, right? So minus sine theta, sine beta. Alright, so there's your adding angles formulas for sine and cosine. Put a box around these. These are important. Now, if you know these, you can derive lots and lots of things from them. For example, let's see here. Well, one sort of obvious related thing would be the tangent of theta plus beta, right? So that would be sine theta plus beta divided by cosine theta plus beta. And so using these, that gives you sine theta cosine beta plus cosine theta sine beta divided by cos theta cos beta minus sine theta sine beta. Alright, and then if you take this, right, and you multiply by 1 over cos theta cos beta, something pretty neat happens. Now, of course, this is only a reasonable thing to multiply by when both cosine theta and cosine beta are non-zero. Okay, but given that condition, we can do this, and when you do that, some really neat simplification happens, right? You can see it when you multiply this times that. The cosine betas cancel. It gives you tangent theta. When you multiply this times that, the cosine thetas cancel. You get tangent beta. Downstairs, right, you get 1 minus, and then the product of the tangents. So there you have it. That is the adding angles formula for tangent. Now, once you know these adding angles formulas, it's pretty easy to derive double angle formulas, right? For example, if you look at theta equals to beta, you can get kind of 3 different sort of nice results. I mean, they require a certain amount of finesse to get what you want. I mean, this one requires not too much finesse. Sine of 2 theta is sine theta cosine theta plus cosine theta sine theta. So therefore, sine 2 theta is equal to 2 sine theta cosine theta, right? So that's pretty nice. To get the let's see what pops out of the cosine formula when we put theta equal to beta. We get cosine of 2 theta equals to cosine squared theta minus sine squared theta. All right. But we know, I mean, everybody remembers sine squared plus cosine squared is 1. So this can be rewritten as cosine squared theta minus parentheses 1 minus cosine squared theta, right? AKA 2 cosine squared theta minus 1. So if you solve that for cosine squared, we get cosine squared theta is equal to 1/2 of 1 plus cosine 2 theta which is a nice identity. Of course, we've used that, right? And then, of course, from that, in the fact that sine squared theta plus cosine squared theta equals to 1, or more to the point that sine squared theta is 1 minus cosine squared theta, we get that sine squared theta is equal to 1/2 of 1 minus cosine 2 theta. As I've mentioned to you before, as a quick check on the reasonableness of the two formulas I just boxed in purple, these two guys, if you add these together, they give you back that sine squared plus cosine squared is 1/2 plus 1/2, which is 1, which is good. Now, a lesser known trig identity, perhaps, at least by American students of calculus, is that tangent 2 theta, right? Put theta equals beta in the tangent formula, we get tangent 2 theta is equal to 2 tangent theta. That's kind of funny. And then divided by 1 minus tangent squared theta. So this little identity, that sort of double angle, or depending how you look at it, half angle formula for tangent, is part of what goes into making the so-called Weierstrass substitution, which is a deep and powerful technique. Alright, so those are some of your basics, right? Now, let's see here. That's about, I don't know, that's about all I care to do in this formalism. I mean, honestly, if I wanted to figure out something like, you know, sine theta times the cosine of 3 theta, it just seems just ugly in this way of thinking. Unless you remember a couple of additional formulas. I mean, you can, I suppose. I mean, it would be good to know these formulas, I reckon. Where are those things? I don't personally always have them remembered. No. Well, no. Yeah. Sorry, I was looking at a reference here and it doesn't have what I want. So, I mean, how would you attack something like that in this way of thinking? I mean, there is a formula, all right, for like sine of A times sine of B. Sine of A, I mean, it turns out that sine A times cosine B is equal to something pretty, all right? This ends up being equal to something divided by 2. And it's relatively nice what goes up here. But anyway, I want to turn the page here and show you a different way of thinking. So part 2 here, I want to show you my actually preferred method of deriving trig identities, which is to use Euler's formula. E to the I theta, all right, is equal to cosine theta plus I sine theta, where I squared is equal to -1. I'm not going to try to motivate this formula for you. It has plenty of motivation. If you go on, just take it for what it is, which is true. Okay, so like, if I know this, I also happen to have that e to the minus I theta is cosine of theta minus I sine theta, where I'm using the fact that cosine's even and sine is odd to pull out that minus. So once I know this and that, I can add these, right? Excuse me. And that gives me e to the I theta plus e to the minus I theta. The sines cancel with the i's, and you get 2 cosine theta. And e to the I theta minus e to the minus I theta gives you 2i sine theta. Alright, either adding or subtracting those. And, alright, so once you know that, then we're off to the races, see, because now we have that cosine theta is 1/2 e to the I theta plus e to the minus I theta, and sine theta is 1/2i e to the I theta minus e to the minus I theta. Alright, and basically what I'm going to tell you is this: if you know Euler's identity, which is this up here, right? So Euler's identity, which relates the imaginary exponential to sine and cosine. If you know Euler's identity, and you have faith in the fact that imaginary exponentials follow the usual laws of algebra, if you believe those two things, you can derive just about everything. Let's see, let me give you a flavor of this. Let's see here. So, for example, suppose I want to figure out what's the identity, excuse me, for, so let's see, example 1. I showed you how to find the cosine squared identity a second ago, right? So let's do cosine squared theta in terms of imaginary exponential. So I start with what I want to simplify, cosine squared theta. Then I replace it with the corresponding expression in terms of imaginary exponentials. All right, then I square it. So that gives me 1/4. And then I've got e to the I theta, plus e to the I theta, e to the minus I theta, plus e to the minus I theta, e to the I theta, plus e to the minus I theta, e to the minus I theta, just distributing out that product, okay? And of course, these two things give us e to the I theta and e to the minus I theta, just these are reciprocals. And so I get 1/4 of e to the 2I theta plus e to the minus 2I theta, that's the first and the last terms, plus 2. I'll just write it as plus 2 over 4, all right? So in other words, I get 1/2 plus 1/2, I'll put this second now, 1/2 e to the 2I theta plus e to the minus 2I theta. I'm really writing a little bit more than I need to here. And, all right, so that's 1/2 plus 1/2. What is this? Well, if you go back to what I boxed in green a second ago, and you replace theta with 2 theta, you'll see we've got exactly cosine of 2 theta. Therefore, cosine squared theta is 1/2 of 1 plus cosine 2 theta. And you can derive the identity for sine squared much the same way. All right? Let me show you some more examples of this method. All right, so I had mentioned that there's a pretty formula involving cosine, like sine A times cosine B. Let's derive it in this way. So I want to say sine of A times the cosine of B. What's the formula for that? All right, so sine of A is 1 over 2I e to the IA plus, oh, goodness gracious, minus sine, minus e to the minus IA, 1/2 e to the IB plus e to the minus IB. All right, so that gives me 1 over 4I. All right, and I'm gonna do the algebra. So this is e to the IA plus IB, so I can write that as I times A plus B. That is from multiplying this term times that term. I'll use some color coding here. All right, then I'm going to do the last one. This times that. So that gives me minus e to the minus I times A plus B, factored out the minus. All right, next I'm going to do the product of this and that. So that is plus what? And then I'll do one over here, like so. All right, so we have e to the I A minus B. And then finally minus e to the minus I, because I kind of see the pattern, right? So minus I times A. This would be plus B, but minus a minus gives me that, right? Aha, well that's very nice, because now I've got 1 over 2I. I'm gonna pull a halfway out over here. Sorry, I should have put it first. Oh well. e to the I a plus b minus e to the minus I a plus b plus 1 over 2i e to the I a minus b minus e to the minus I times a minus b, and that's all. I pulled the half out. But again, if you go back to the formula, that the sine of theta is 1 over 2i rather, e to the I theta minus e to the minus I theta, right? And you identify here we've got theta equals to a plus b, and here we've got theta equals to a minus b. Then what we just have derived is that this is equal to 1/2 sine of a plus b plus 1/2 of the sine of a minus b, right? Or let me just write it kind of in a more pretty kind of way. So we've got sine of a times the cosine of b is equal to 1/2 sine of a plus b plus the sine of a minus b. Now I'm sure you could derive that from, you know, the adding angles formulas and other things in real trigonometry. I just find this to be very, very nice that we can derive it straight away from laws of algebra and that one crucial assumption, Euler's identity, right? Which, by the way, has beautiful justifications in terms of complex geometry anyway, so it's not like it's something that's mystical, it's just something whose explanation is slightly outside what I should talk about at the moment. But anyway, it's a worthwhile thing to know. Now, once I know that, of course, I can differentiate this with respect to b, or with respect, I'll differentiate with respect to a. If I differentiate this with respect to a, that gives me what? Cosine a, cosine b, right, is equal to 1/2 of what? Cosine a plus b plus the sine of, I'm an idiot, cosine of a minus b. So there's another identity, product of cosines, product, oh my goodness, did I do that right? DDA, cosine, yeah, sorry. So there's an identity, let's see, I got sine, cosine, 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 how about sine, sine? Well, sine, sine I can also get from differentiating, right? Just instead of differentiating with respect to a, I differentiate with respect to b, right? And that's going to give me minus sine a, sine b is equal to 1/2, be careful, I'm supposed to differentiate this one, right? Cosine of a plus b, and then the chain rule brings a minus out here. I'm differentiating this with respect to b, so I get cosine of a minus b. And again, I pulled the minus out because of the chain rule. And so, what does that give us? Well, that gives us sine a, sine b is equal to what? 1/2, right? The cosine of a minus b minus the cosine of a plus b. And so these product formulas are really quite neat. They explain things like beats in music and other things. They're very important identities to know about if you're doing analysis of waves and things. All right, so there's a couple of sort of showcases. Let me see if I can think of something else here. The other really cool thing about the imaginary exponential is de Moivre's theorem, I suppose. So I'm probably spelling this. So that is basically this. Well, here's what it looks like for the imaginary exponential. E to the I theta to the n power is equal to e to the I n theta. It's that's okay, that's it. So what's that look like? What's that mean in terms of cosine and sine? That means that cosine of theta plus I sine theta, right, to the n power is equal to the cosine of n theta plus I times the sine of n theta. And then so if you just start, looking at what this tells you, it tells you all kinds of stuff pretty fast. I'm not quite as big a fan of this as I am of what I showed you in example 2, because example 2 is just so direct, and we're starting to get into indirect identities again, but, whatever. If you look at n squared, so we got cosine theta plus I sine theta times cosine theta plus I sine theta is equal to the cosine of 2 theta plus I times the sine of 2 theta. This is a complex equation, all right? Now if I multiply this out, I get myself a cosine squared theta. I times I is minus 1, so minus sine squared theta, plus I times cosine sine plus sine cosine, so it's plus 2 cosine theta sine theta, right? So that's equal. And then the beautiful thing about complex equations is every complex equation gives you 2 real equations. So like this has to be equal to that, and this has to be equal to that without the I. And so, hey, there's our friends. Cosine of 2 theta equal to cosine squared theta minus sine squared theta. That was an identity we saw before. And of course, the sine of 2 theta is equal to 2 sine theta cosine theta. So it's kind of fun in a pinch. N equals 3. That will give us something a little bit weirder. N equals to 3, so you gotta, look at cosine theta plus I sine theta cubed equal to cosine 3 theta plus I, the sine of 3 theta. And if we do that, right, I'm going to do in between step. Think about this being A and this being B, the whole thing with the I. And the cube, of course, is A cubed plus 3 A squared B plus 3AB squared plus B cubed, right? Now that's actually going to be equal to cosine cubed theta. A squared, that's 3 cosine squared theta, 3I cosine squared theta sine theta plus thrice 3 cosine theta. B squared is an I squared, so that's a minus sine squared theta. And then plus B cubed is going to be actually minus I sine cubed theta. So, collecting stuff here. Keep the real part, cosine cubed theta minus 3 cosine theta sine squared theta plus I times 3 cosine squared theta sine theta minus sine cubed theta. So apparently this is equal to that, and this is equal to that. So there you go, cosine of 3 theta is cosine cubed theta minus 3 times cosine squared theta, cosine theta times sine squared theta. And the sine of 3 theta is equal to, you notice the I is just an in-between thing. It's just a device to derive identities. It goes away in the final product, just like the quadratic formula involves an I, right? But it's just, it has something to say about a real thing. This is typical of complex calculations. We use imaginary numbers to achieve some goal, and then at the end of it, it's not there, at least not explicitly. It's just working in the background. So, such as this. So there's a couple of things. You can keep going, right? And of course, you can rewrite these in other ways. Let's see here. What else should I show you? Oh, the other pretty neat thing about imaginary exponentials, if I looked at e to the I theta times e to the I beta, right? Well, you would hope that that would be e to the I theta plus beta, right? What does this mean? Well, that's cosine theta plus I sine theta. And that's cosine beta plus I sine beta by Euler's identity, which we're taking on faith at the moment. And then that's cosine of theta plus beta plus I times the sine of theta plus beta. But if you multiply this out, what do you got? You got cosine theta, cosine beta minus sine theta sine beta, because I squared is minus 1, plus the imaginary part, I times, well, over there you got cosine theta sine beta plus sine theta cosine beta, right? And so this, of course, sorry, well, this is, scratch that, I can write it again, is equal to cosine theta plus beta plus I times sine theta plus beta, and I hope you can see this is equal to that, and this is equal to that. Now we took those things as basic in the other method and used these to derive other things, but now you see the Euler identity and the laws of exponents that we're assuming hold for imaginary exponentials straight away derive adding angles formulas like that. Now, okay, I mean, to be serious for a second here, when you study complex analysis, the fact that we know the adding angles formulas for sine and cosine are what provide, from one perspective, the definition and existence of the imaginary exponential. But it depends on what you take basic. If you define the imaginary exponential in terms of power series, then I guess you don't need to know. Then this is again a derived result. But which came first, chicken or egg? I don't know. Probably the chicken, really. But let's see here. Anything else? Well, there's more, of course, to say about the method of phasors and adding sine functions and cosine functions using imaginary representations. But I think that's all we really need for calculus 2, at least as a I hope this helps you as a method for remembering some of these identities and possibly deriving ones you forget. It helps me anyway. So that's a pretty good slice of it. I think I'm going to stop here. Of course, there's more to say. If you look at the chapter 2 of my notes, I do have a derivation in there about how to add waves using imaginary exponentials. So if you want to talk to me about that, you're welcome to come and talk to me in office hours, whatever. So the remaining video that I have to make for you guys is on epsilons and deltas and the careful definition of a limit. So I'll do that last. Thanks, guys.